Hey guys, this video is a brief introduction to nuclear chemistry. Brief introduction because nuclear chemistry is a fairly complex topic, and so we just hit on some of the highlights in this course here. That's what we're going to do. So let's start talking about subatomic particles. The symbol for a subatomic particle, particles inside of the atom, look like this, where Z is the symbol, X is called the mass number, and Y is the charge number. So these are the common ones, the ones that we're going to see. A proton has, so any of these symbols, by the way, work, right? So all of these subatomic particles we have more than one way of representing them. So a proton has a mass number of 1 and a charge number of 1, and any of these symbols mean that. Electron or a beta particle, mass number of 0, charge number of -1. There is a technical difference between an electron and a beta particle, and we're not going to really worry about it, but it is we're the source of the particle. If it's produced from the nucleus during radioactive decay, we call it a beta particle. If it exists already outside of the nucleus, say a 1s orbit or something, then it's an electron. And one of the things that a nucleus can do is can capture an electron from an orbital and then undergo a nuclear reaction. A positron has a mass number of 0, just like a beta particle or an electron, but a charge number of +1. And an alpha particle has a mass number of 4, charge number of 2. Neutron, mass number of 1, charge number of 0, no charge. So a nuclear equation describes a nuclear reaction. And during a nuclear reaction, the law of conservation of mass, so mass must be conserved and charge must also be conserved. So we can use that to predict a missing particle, which is what we're going to do here. The idea being that the sum of all of the mass numbers on the left side of the arrow must equal the sum of all the mass numbers on the right side of the arrow. Similarly, the sum of the charge numbers on the left side of the arrow must add up to equal the sum of the charge numbers on the right side of the arrow. So like, for example, in this first nuclear equation here, there's just one mass number on the left, 135 from iodine 135. And on the right, we have xenon 135, mass number of 135, plus some other particle. That's what that blank means. And so we know that the mass number for this particle must be 0. And then we can do the same thing with the charge number to get the charge number. And once we know the mass number and the charge number, that's going to be unique to one of those subatomic particles. So you just find the subatomic particle that has that set of numbers, mass number and charge number. So why don't you guys give this a shot, see if you can fill in the blanks, and pause the video and then come back when you get your answer. Welcome back, guys. So for the first one, the decay of iodine 135, on the left the mass number is 135, and the right 135 plus X, whatever it is here. Well, X has to be equal to 0. Good, we know the mass number. Doing the same thing with the charge numbers, this iodine has a charge number of 53. On the right, we have 54 from xenon plus Y. Well, that means Y has to equal -1. So now that we know what the mass number and the charge number are, 0 and -1, we see that a beta particle, or an electron, is the only particle that has that set of mass numbers, so we know what the missing particle is. Technically, because it's produced during the radioactive decay, it would be called a beta particle, but you could use E-2 or anything like any of these symbols would be fine. The next one, this is called neutron bombardment, where we hit a nucleus of cobalt-59 with a neutron. And so doing the same thing, the mass numbers on the left, 59 plus 1 add up to 60. On the right, 56 plus X, X has to be 4. Doing the charge numbers, 27 plus 0 equals 25 plus Y, Y is 2. So the subatomic particle that has these set of mass and charge numbers, 4 and 2, is an alpha particle. So we know that the missing particle is an alpha particle, and we could write it like this. Write it down here. And the next one. So again, neutron bombardment of uranium-235, and we're producing krypton-94, barium-139, plus another particle. So doing the mass numbers on the left, 235 plus 1 is 236, 94 plus 139 plus X, X is 3. Doing the charge numbers, 92 plus 0, 92, 36 plus 56 is 92, so Y equals 0. Well, You see, we don't have anything that has a mass number of 3 and a charge number of 0, but we only have one particle, subatomic particle, that has a charge number of 0. That's a neutron. That means what must be happening here is we must be producing 3 neutrons. So we could write 3 neutrons like this or like this, and this looks like that. This way you see that the mass numbers add up to be 3 times 1 is 3, plus 139 plus 94 is 236. There we go. So one other thing real quick, guys. Another thing we can do, we can figure out if we don't know what the daughter nucleus, we call these daughter nuclei, is once we figure out what the charge number is, that's for an isotope, that's the same as the atomic number. So if we figured out, like we were given that this was 3 neutrons over here, we could figure out this was krypton because the missing charge number would be 36. So we just go to the periodic table, find atomic number 36, and see, aha, that's krypton. And the mass numbers would give us the isotope. Nuclear stability, or I guess instability. So nucleus, we know, is very dense, and there's protons in every nucleus. And these protons all have positive electric charges, and they're very close to each other. I mean, very close. So there's a lot of coulombic repulsion. They're pushing each other apart really hard. But we know that nuclei are stable, many of them. And that means something else must be holding those nuclear particles, the neutrons and the protons, all together. And it ends up there's a short-range attractive force between the nucleons. That's what we call protons and neutrons, nucleons. And we're not going to get into all the weak nuclear force, strong nuclear force, and all that stuff. That's for physicists mostly, or nuclear chemists, I guess. But we're just going to say there's a strong attractive force. And so basically what happens, and there's other things that can happen, but basically what happens is if the repulsion overcomes the attraction, then this is going to be an unstable nucleus, and it'll eventually decay or disintegrate, emitting particles or radiation. Gamma radiation, I didn't show the symbol for that, it's just a symbol gamma. That's also something, it's electromagnetic radiation that can also be produced in a nuclear decay. So for example, the decay of uranium-238 produces an alpha particle plus some other particle, and if we add up the mass numbers and the charge numbers, just like we did a minute ago, we see that the other missing particle is thorium-234. We know it's thorium because we know that the charge number must be 90, and so we look on the periodic table, we find atomic number 90, and we see, aha, that's thorium. And then thorium, once it's produced, that decays farther, and we see that it produces another nucleus and a missing particle here. If we add up the mass numbers and the charge numbers, we see that it's a beta particle that's missing. So there are patterns to nuclear stability. And one of the predictors of whether or not a nucleus is stable is the neutron to proton ratio. And that's what this graph over here is showing, okay? It's showing the neutron to proton ratio for a lot of different isotopes. For example, down here, lithium-6, there's 3 protons, 3 neutrons, the ratio is 1 to 1. These red dots are the zone of stability is what we call it. Cadmium-110, the ratio is 1.29 to 1, and mercury-202, 1.53 to 1. And so this straight line here is what you would have for a 1-to-1 neutron to proton ratio. If a nucleus, if an isotope is outside of this band of stability, then it's going to be unstable and it will decay. And this is a useful thing to know. If it's in this region out here, if the neutron to proton ratio is too high, has too many neutrons, and one of the things that it tends to do is decay spontaneously by beta production or beta emission. It gives off a beta particle. Whereas if it's down here, then the neutron to proton ratio is too low. There's too many protons relative to the number of neutrons. And so it will decay, and one of the things it can do, it's common for nuclei that fall down here to undergo positron production, or emission. It gives off a positron. So there's some guidelines, rules of thumb here for predicting whether or not a nucleus is stable. And it ends up there are more nuclei that are stable that contain these magic numbers of protons or neutrons than nuclei that don't have one of these numbers of protons or neutrons. The numbers are 2, 8, 20, 50, 82, and 126. There's also many more stable nuclei that have even numbers of both protons and neutrons than with odd numbers of neutrons and protons. All isotopes of elements that have higher atomic numbers than 83. So 83 is bismuth. So polonium and above, they're all radioactive to one extent or the other. Also, technetium, Tc, and promethium, Pm, are all both radioactive. So this is just kind of showing what it says up here. If we have odd numbers of both protons and neutrons, there's only 4 stable isotopes like that. Whereas if we have an even number of neutrons and odd number of protons, we have about 50 of those, even protons, odd neutrons, 53. Both of them even, that's what this one's saying right here, 164, so a lot more like that. So this is what I was saying a minute ago about the belt or the zone of stability. So nuclei that are above the belt of stability, zone of stability, the neutron to proton ratio is too high and they undergo beta emission. And here's what beta emission looks like. Basically, a neutron within the nucleus is converted into a proton, decays and leaves behind a proton, and emits a beta particle. You see how the mass numbers and charge numbers add up? 1 over here, 1 and 0, so 1 over here. Charge number 0 here, 1, -1, 0 here. So this shoots out a beta particle. An example of this would be iodine 135, like we saw, going to xenon 135 and a beta particle. Now, if a nucleus, an isotope, is below the zone of stability, then the ratio of neutrons to protons is too low, and they undergo positron emission, or they can undergo electron capture. And so when they do that, see, the idea is they end up, after these two processes, back in the zone of stability. So positron emission looks like this. A proton in the nucleus decays and forms a neutron. So we're increasing the neutron to proton ratio, and it produces a beta particle. Again, the mass numbers and charge numbers add up. An example would be potassium 38 decaying to argon 38 and a positron. Electron capture looks like this. A proton in the nucleus captures an electron, probably from a 1s orbital, and is converted into a neutron. So once more, the neutron to proton ratio increases. An example would be iron 55 capturing one of its electrons, being converted into manganese 55, right, like this. Okay, so thermodynamic stability of nuclei. So we're going to start out with an example. And we're going to imagine that we can build an oxygen-16 nucleus from its constituent protons and neutrons. So oxygen-16 has 8 protons and 8 neutrons. I give you the mass in grams of protons, neutrons, and electrons over here. And so if we add up the mass of the 8 neutrons and the 8 protons, it adds up to be this number right here, 2.67805 times 10 to the minus 23 grams. Now we know from experiments measuring it that the actual mass of an oxygen-16 nucleus is 2.65535 times 10 to the minus 23 grams. Not exactly the same, and this looks like, I know, a small difference, but it's actually really important. We'll see how important it is in a minute. So let's look at the difference in mass for one nucleus of oxygen-16 between the mass that it actually is and the mass that we calculate. And the difference is 2.269 times 10 to the minus 25th grams. So or negative, because we take what it really is minus what we calculated it would be. And so that means for 1 mole of oxygen-16 nuclei, the difference is negative 2.269 times 10 to the minus 25th grams per nucleus times Avogadro's number of nuclei per mole is negative 1.1366 grams per mole. That's something we can measure, okay? This difference, this number right here for oxygen 16 or for whatever the nucleus is called the mass defect. Okay. By the way, you do not have to memorize any of these masses. I will give them to you when you need them. So what happens to this mass? We know that mass can be neither created nor destroyed. Well, it ends up that Einstein told us that mass and energy are interconvertible, right? They're basically the same thing. And so he said E equals mc squared. Energy is equal to mass times the speed of light squared. Remember, speed of light is 2.998 times 10 to the 8th meters per second. So the change in mass corresponds to a change in energy, or delta E equals delta mc squared. So we know delta M, we just calculated it for the formation of, for our thought experiment of forming an oxygen 16 nucleus from its constituent protons and neutrons. So the change in mass was negative, and I converted this to kilograms per mole, by the way, by dividing by 1,000. Plug that in, multiply by the speed of light squared. And the reason I converted this to kilograms per mole is because if you look at the units here, we get kilograms meters squared per mole second squared. Well, remember, kilograms meters squared per second squared is joules. And so we wanted a unit of energy that we're familiar with, and that's why we're using kilograms here. But we see that the change in energy, the difference in energy, when we form a nucleus of oxygen 16 from its constituent components, the protons and neutrons, and its actual mass, that energy, that difference in mass is released as energy, this much energy. And so now, this is a lot of, pretty lot of energy, like 10 to the 10th kilojoules, right? Which is an enormous amount of energy. So one of the things that we do and that they do in nuclear chemistry is they talk about the change in energy like per nucleon. A nucleon, remember, is a proton and a neutron. So to find the change in energy for our oxygen 16 nucleus per nucleon, all we do is take the change in energy and convert back to one nucleus by dividing by Avogadro's number and then dividing by the number of nucleons. So this 16 here, guys, this comes from 8 protons plus 8 neutrons, right? And so we see it's negative 1.275 times 10 to the minus 12 joules per nucleon. It's a common way of talking about this energy. This energy is called the binding energy, by the way. Because what that tells us, okay, so in our thought experiment, right, we formed this nucleus from the protons and neutrons that make it up. And we calculated, just based on the mass defect, how much energy would be released when we did that. But that also tells us exactly the number to go the opposite way. How much energy would it take to decompose, to break apart this nucleus into protons and neutrons? Well, we'd have to put in that much energy, right? That's called the binding energy. And it's common to give binding energies in terms of a unit called mega electron volts, MeV. So here's the conversion right here between joules and mega electron volts. 1 mega electron volt is 1.602 times 10 to the minus 13th joules. So that binding energy also tells us how stable a nucleus is. So this graph here shows the binding energy per nucleon, the kind of thing we calculate, for some of the elements, versus the mass number. So we start with hydrogen, and we go up, right? And what happens is we go up, and then it goes down, and all these little weird things happen. But we reach a maximum up here. And iron 56 is the most stable nucleus. And so after that, they become less stable, right? The binding energy decreases. They're not held together as strongly. And this has implications for, what goes on inside of stars and all this stuff. But that's a different class. All right. So here's an example. Calculate the binding energy. So we just did something like this. You've seen it before. In mega electron volts per nucleon for lithium-6. And so what we're going to do here is we're going to use units of, we're going to give you the units in AMUs and grams. And so these are some conversion factors that you may need. and I'm telling you that the mass of a single atom of lithium-6, that isotope, is this number, 6.015122 AMUs, remember atomic mass units. And so with this information, you have enough information to calculate the binding energy in mega electron volts per nucleon. So see if you guys can figure that out. Go ahead and work on that. Pause the video and come on back when you're done. We'll work it out. Welcome back, guys. So let's find the, first thing we're going to do is, just like we did with oxygen-16, is add up the masses of all the protons and the neutrons. And now we can do this in whatever units we want to. We saw that in grams with oxygen-16. I'm going to use AMUs. I think AMUs actually are a little bit easier to use because they're numbers that aren't, exponential, right? So because lithium-6 has 3 protons and 3 neutrons, and I gave you the mass of those 2 subatomic particles in the previous page, I'm going to use the mass in AMUs, the 3 protons and this mass per proton plus neutrons, and so it's 6.047823 AMUs. All right, so now we're going to look at the mass defect. This is just the difference. So we were told, so you have to be told this. The actual mass of this isotope is this number right here, 6.015122 AMUs. Subtract the mass of the sum of the masses of the nucleons, and we get a negative 0.032701 AMUs. And so, again, this is how much mass would be converted into energy if one atom of lithium-6 were formed from its protons and neutrons. And it's also the binding energy, how much energy it would take to break apart this nucleus. And so we use Einstein's equation to calculate what this energy is, right? Because remember, we want binding energy per nucleon. So we're going to get delta E. And so because I used AMUs, and I like to use AMUs up to that point, but remember, because of the way the units work out, we're going to have to convert the AMUs to kilograms. So I'm going to take my mass defect in AMUs, convert it to kilograms. I gave you this conversion on the previous page. And so we have the mass defect in kilograms. All right, great. We can plug it into Einstein's equation, E equals mc squared. And we see that the binding energy, the difference in energy is negative 4.881 times 10 to the minus 12 joules. So the negative sign here comes about because of our negative sign right here. But when we're talking about binding energies are all positive numbers, how much energy we have to put in. So it's just the positive, there would be positive 4.881 times 10 to the minus 12. But we're not done, because this is for a single atom, and we want per nucleon. So all we do is divide by the number of nucleons, and we also, we're asked to have it in mega electron volts, so we just do that conversion. So we take the binding energy per atom times 6 nucleons in one atom, and we get the binding energy per nucleon in joules per nucleon, and we just use the conversion factor I gave you to convert to mega electron volts. And we see that the binding energy is 5.078 mega electron volts per nucleon for lithium-6. All right, so radioactive decay. This is underlying all this stuff that we're talking about. We know that nuclei that are outside of the belt of stability undergo spontaneous emission, and they can emit particles, all the particles we've talked about, electromagnetic radiation, or both. That's what we mean when we say radioactivity. The primary types of radioactivity are alpha emission, so it produces an alpha particle. Beta emission, it produces a beta particle. Gamma emission, this is electromagnetic radiation, so photons, very, very high energy photons called gamma rays. Positron emission, or electron capture, which is usually a 1s electron that's captured. So also, when a nucleus decays, a lot of times that's not the end of the story. The nucleus that's the daughter nucleus, the one that's produced, that decays, and then its daughter nucleus decays, and so we get this sequence of nuclear reactions until we end up falling into that belt of stability and we get a stable isotope. Sometimes it's a fairly long process. For example, uranium-238. This is the decay series for uranium-238. So if we start up here with uranium-238, It spontaneously gives off an alpha particle to make thorium-234, which undergoes beta emission, and then another beta emission, and then an alpha particle, alpha emission, alpha, 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 beta. So there's no way that, I expect you guys to memorize this, because it's different for each nucleus. But this is just an example so you have an idea of what a decay series looks like. So kinetics. So we've studied kinetics before, and it ends up that radioactive decay is all first order kinetics, which is really nice because that's pretty simple. And if you think about that, it makes sense. And we're not talking about bombardment here, we're talking about just decay. So decay, it's just one nucleus, right? So there's only, it's the order is going to have to be 1, right? And so it's first order kinetics. And so that means we've seen this equation before. The first order, the integrated rate law for first order decay kinetics is natural log of n over n0 equals negative kt, where n is how many nuclei in this context, n is the number of nuclei that remain after time t. N0 is how much we started with, how many nuclides we call them we started with, and k is the rate constant. Also, we have half-life, just like we saw back in kinetics. Half-life, it's defined as the time required for half the nuclides to originally present to decay. And so the half-life, again, the way we get the half-life, the formula here is we say n is equal to 1/2 n0. The n0's cancel, we get natural log of 1/2. You guys have seen all this, and it ends up rearranges to this. And so these graphs are just depicting the half-life of strontium-90 and then molybdenum-99. So the thing about first order kinetics is the half-life is the same for each decay, right? So if the half-life is 28.9 years for the first half-life, it's 28.9 years for the second and third and fourth and continuous, something like that. So each half-life, the amount decreases by 1/2. So we start out with 10 grams of strontium-90. After one half-life, we have 5 grams. After 2 half-lives, we have 2.5 grams, and so on. This is just another example. This we start with here the half-life for molybdenum-99 would be 66 hours, right? So we start with 1 milligram. After 66 hours, we have 1/2 milligram, and so on. So this is a logarithmic curve right here. So a couple of examples for us. First, we can define something called the third life, just like we did the half-life. And so what I'd like you guys to do is see if you can figure out what the third life is for a nuclide that has a half-life of 28.9 years, strontium-90 like we just saw. So you go ahead and play with that equation, natural log of n over n0 equals negative kt. And see if you can get a formula for the third life, and then use that to get the value for the third life, given that the half-life is 28.9 years. So go ahead and pause the video and come on back when you get your answers. Welcome back, guys. All right, so what we're going to do is, the third life would be when n is equal to, so the amount that's left is 1/3 of the original amount. That's what this looks like here. So when we plug that into our integrated first order rate law, natural log of 1/3 n0 over n0, the n0's cancel, we get natural log of 1/3, which is the same as negative natural log of 3, which is equal to negative kt. Or, negative signs cancel, cross, pull the k over here, and we get our formula for the third life. Natural log of 3 over k is equal to the third life, 1t 1/3. So what we're going to do is you're going to use the given half-life to find the rate constant k. And so rearranging this, the rate constant equals natural log of 2 over the half-life, and we were told that the half-life is 28.9 years. So we get the rate constant is 0.02398 or 0.0240 per year, inverse years. Now we use this and plug this up here into our equation we derived for the third life, and we see that when we plug this in, we get the third life is 45.8 years. So, and that makes sense, right? It takes longer to decay down to 1/3 of its original amount than it did 1/2 of its original amount, which is half-life. And now another example. plutonium-239, which is one of the radioactive isotopes produced in what are called breeder reactors, has a half-life of 24,100 years. That, pretty long time, right? So how long will it take for a sample of plutonium-239, so radioactive waste, right? That's what we're talking about here, to decay to 0.1% of its original value. So basically we're just we're going to use the half-life equation to find the rate constant, and then from the rate constant we're going to use the integrated first order rate law to find when n over n0 is 0.1%. So why don't you guys work this out and come on back when you get your answers. Welcome back, guys. So let's use the half-life to find the rate constant. So there's the rearranged half-life equation, plugging in 24,100 years for the half-life. We see that this is actually supposed to be a negative sign right here. That the half-life is 2.88 times 10 to the minus fifth per year, inverse years. And so, okay, so there we go. We have the rate constant. 0.10% of its original value means that n is equal to 0.1%, so 0.1 over 100 times n0, or rearranging this, n over n0 equals 0.0010. And so now we can just plug in natural log of n over n0 equals natural log of 0.0010 equals negative k, which we found, times the time. So we rearrange this, solve for the time, and we see that it takes 240,000 years for that radioactive waste to decay to a low enough level to where it's not a problem, which is one of the big problems with radioactive waste. Although there's a lot of good things about nuclear energy too. That's all there is to that, guys.